Requesting connection. Established. Encrypted. We're live. The show you've been asking for. Advice, technology, and community. Linux first, all others second. This is Ask Noah.
Live Multispeed Technologies, the Ask Noah show starts right now. This is the show where we came to do all the things on Linux they said couldn't be done and take your questions on how to do the same. The phone lines are open this hour. Be a part of the program. It is a free call, 1-855-450-NOAH. It's 1-855-450-6624, or send an email to live@asknoahshow.com. My name is Noah Chalaya. I am your host, delighted to be here with you as another episode of the Ask Noah show kicks off this hour. Our first email comes in tonight from Scott. Scott says, "Hi Noah, thanks for the network segment on your show recently. It prompted a few questions that I have on my network. I have a Cisco C2960S 48TS-L switch that I'm running on the LAN-based SDM. Can you explain what a management VLAN is and how it differs from any other VLAN? I set up a few VLANs and set the IP address for each one. For example, 192.168.50.1 on VLAN 50. I've discovered that I can access the switch configuration from any VLAN IP. I'd like to allow access to the switch config only from 192.168.99.1 inside VLAN 99. I'm thinking perhaps I don't have the management VLAN set up properly. Would you recommend running a web server in a VLAN, or would I be better off setting up an optional interface in pfSense to segregate the web server? If a VLAN is okay, are there any other rules that I should implement besides the above access list to make sure the LAN is secure from the web server? Thanks for all you do, Scott." So let's step through this a little bit. As far as what a management VLAN is, a management VLAN, and I think you pretty much have this down, a management VLAN is a VLAN that is designed to administrate the network. And so it's something that typically users wouldn't have access to, printers wouldn't have access to, those kinds of things. And it allows you to get into the configuration of the switch and not just utilize the switch. So the management VLAN would have the configuration access, whereas the guest VLAN, they'll still plug into that Cisco 2960 switch, but they can't actually talk to the switch themselves. They can just pass traffic through the switch. As for why you're able to access the 192.168.50 VLAN from the 99 VLAN, I want to stop and back up and just say that a VLAN doesn't necessarily have to have, you don't necessarily have to structure your IP address to include the VLAN tag number in the IP address. So for example, he's using best practice 192.168.50.1 and 50.1 is VLAN 50. You wouldn't have to do that, but it's a nice way to separate out so that you can see just from the IP address what VLAN you're on. So that's kind of an aside, not really directly relevant to your question, but now that we understand that, or we've established that, the reason there are two possible ways that you can solve your management issue. The first thing is that you can restrict in the device to only allow management access on VLAN 99. The other way that you could do that is you could set, well, actually, that is required no matter what you do. So if the switch exists on all of those VLANs and has an interface on each one of those VLANs, and you've not restricted the management side to just .99, then it's not going to work. So that's step one. But I'll throw something else in there. If you did that, you limit the management VLAN to just 99, then you wouldn't be able to access it from .50, and that technically solves your problem. But it creates a new one, or could create a new one anyway. You may have a situation in where you exist not on a management VLAN, you get an IP address just like everyone else does, but you want a specific machine or a specific group of machines to be able to do inter-VLAN routing. And in that event, or that scenario, what you could do is use something like a pfSense, and inside of the firewall rules, create a rule that allows inter-VLAN routing between either an entire VLAN, even if it's not necessarily used for administrative stuff. It may be used for other things, but you want a certain range to be able to send traffic over to the administrative VLAN, or you can block it all together inside of the firewall and create an additional rule that says, hey, this traffic can never go to any other VLAN. Everything stays the same. And you can, oftentimes we'll see that with not so much management stuff, because that really is kind of you really want to limit who can get to it. But oftentimes you'll start getting into other VLAN stuff where you'll have things like audio over IP or phones, and you want them VLAN, you want them on a separate place, but you also want to be able to, for example, download your voicemail from your computer. And so there's ways to create exceptions to those rules, and there may be an opportunity to do that or a reason to do that. Would I recommend running a web server in a VLAN? Yeah, I absolutely would. Would you be better off setting an optional interface in pfSense? You could, but bear in mind, when you're creating a separate interface in pfSense, essentially what you're doing is changing the configuration in pfSense to have two interfaces acting as separate interfaces on separate networks. Recall that when we set up VLANs, really what we're doing is setting up a switch to have separate interfaces on separate networks. And so to a certain degree, you're doing the same thing. You're just kind of approaching it from a different angle. To bring that home a little bit more, you could set up one of your pfSense's four networks. Actually, you could have one on VLAN 10, one on VLAN 20, one on VLAN 30, and one on VLAN 40. Or you could create a trunk port and pass all four of those VLANs out of pfSense on a single interface and break them out on the switch. Why I point that out, or why that's of note, is because if you're using something like the SG1100, that only has a single LAN port. It has a WAN port, a LAN port. I think there's an OPT port on there, but I'm not quite sure. And in that scenario, if you're doing more than one or two LANs, you have no choice but to break them out on the switch. But the powerfulness of pfSense and in fact the beauty of VLANs is that doesn't matter. You can have 50 networks, you can have 48 networks on an SG1100, and you can have a single trunk cable that goes from your SG1100 out to your HP 48 port switch, your Cisco 48 port switch, and then you can break them all out from there and have 48 separate networks on the switch. You can do that all with VLANs. So absolutely the right way to go. As far as the actual web server, the way I would set that up is the web server should have an interface that is connected and either has a public IP or sitting behind the firewall, whichever you want to do. And then ideally a second network card that is either tied to the VLAN that is doing the database stuff or whatever the web server is referencing. And so if the web server is just serving up web pages, yeah, have its own IP address, have it out in its own little world. But if it needs to access other things, if it needs to pull, a MySQL DB, that doesn't necessarily need to be on the internet. But you can put a second network interface and have the web server and the MySQL server talk on a network that isn't directly exposed to the internet. And then that way you're beginning to limit your threat vector. Again, there's a way in, right? If they compromise the web server, they'll be able to get to the rest of the network, but it gives you one extra step of protection. But absolutely the way I would go. Thanks, Scott. I appreciate the email. Our second email comes in from Charlie. Charlie writes in and says, "Good day, Ask Noah and community. With all of the informations and rumors about the Unify company, what is your impression about replacing Unify gear with TP-Link Omada? I found 3 different creators on SensorTube talking about it, and it seems like you can self-host your own controller along with it. I've not tried into the cloud or app. Could the Omega gear handle large volumes of connections, or are they only suitable for home, small office?" Charlie. Well, Charlie, I've not played with the TP-Link Omada, but I do have one on the way, and I'm going to check it out, and I'll get back to you. I am interested in other alternatives into Unify, if only because I think the more competition that's out there, the better all of the products are going to be. Our third email comes in from Paul. Paul writes in and says, "Hi, Noah. I love the show. I've been trying to access your WireGuard tutorial," and then he gives a link that's probably included in the WireGuard tutorial. He says, "The webpage never loads. I tried last week and today. I've tried on both Firefox and Chromium." Well, Paul, I apologize. It's not your fault. It's my fault. We have since updated the server since I've created that tutorial. And so the URL has been updated for that tutorial. And so I will include a link for you in the show notes, as well as we'll go back. If you tell me where you found that, if it was on YouTube, we'll go and update that link there as well. Our fourth email comes in from Nick. Nick says, "Hey Noah, Nick here. Several weeks ago, you answered my question about Fedora, and I'm really thankful. Now I have another one for you. What home router would you recommend for a small household, 2 people who work from home? A little backstory. I own a Ubiquiti Edge router Lite, but last week its USB storage died. Prior to that, the Edge router had been working just fine, and I can change the USB, but honestly, I've been looking for a reason to replace it because I don't like how Ubiquiti is doing business lately. I was looking for a pfSense appliance or a Microtex hex router, but I don't have any real experience with any of them. Also, would you recommend any of the consumer brands? Right now, I'm using a cheap TP-Link Archer as a stopgap measure. The thing doesn't even have gigabit, but it's been rock solid so far. As always, keep up the good work. All the best from the other side of Europe, Nick. So, Nick, I will tell you, my kids, there is a network in our house called Technology. The whole idea is to allow my kids to be able to explore the internet and network technology without having to run into the fact that their dad owns an IT company. I try to be very conscious about the fact that just because I can do things doesn't mean I should. And the way I've done that is with a TP-Link system. I use TP-Link in my own house. If I was looking for a better, more commercial grade router, I'd highly recommend you check out the SG1100. It's a $200 router from Netgate. It's going to do all of the things right out of the box, and it gives you the opportunity to grow when you need it. Like I said, connect to a 48 port switch, get 48 ports. 48 different networks. If you needed to do that, you could. It all happens with the SG1100. I'll have a link for you in the show notes. Our first networking segment was a success. We saw that in the feedback. And so I've invited Steve Ovens to come back on the program. We're going to do round two. We're going to dig a little bit deeper into networking. Steve, welcome back.
Thanks, Noah. Thanks for having me back.
Yeah, thanks for taking the time to do this. It's exciting. So we're going to pick up kind of where we left off. We've given everyone kind of a basic understanding of networking and the concepts and theories necessary to get a basic networking up and running. Even if you don't understand how to tweak that network yet, you'll understand how to go to Best Buy, purchase the equipment you need, plug it in, and make it work, and at least understand what that equipment is doing. Now we're going to dig into what all of the individual switches and levers do and how you can use that information to either play with your network or solve problems. So I want to start with IPv4. Steve, we have a basic understanding of what IP addresses are and how they're used to allow machines to talk to each other. Let's talk a little bit more about some of the more advanced ways that we can use IP addresses to do things with groups of machines, for example, as is in the case of broadcast traffic. So let's start with this. What is broadcast traffic and what is a broadcast domain, and where are those concepts used?
So broadcast traffic is basically where you don't have a specific individual endpoint in mind. And so what happens is the computer will, or the device will send out a traffic that just announces something to the network. So printers are notorious for broadcasting. So what they'll do is they just kind of spam your network with information about them being here. And it's supposed to help with things like auto discovery. So you were asking about a broadcast domain. Broadcast traffic is not forwarded by a router. If you remember last time we talked about how a router is required to do communication across different network segments. So if we've had a VLAN set up or we've done subnetting, a router or a layer 3 switch is required to enable traffic to pass back and forth. Broadcast domain is basically like a fence around your yard, and you can broadcast anything you like inside of your yard, but once it gets to the fence, it stops. So broadcast domain is basically any computer that can hear that broadcast, and routers and layer 3 switches do not forward broadcast packets.
Is there a downside in having a lot of broadcast traffic on a network? Say, for example, I have a lot of printers. I mean, why wouldn't I want my printer to advertise to, every network, every machine, all the way from here to Kingdom Come? Why would we want to limit that?
Well, as you can imagine, if you've got a bunch of things out there just constantly being chatty, as we say, what happens is your network can actually get congested with too much information that is not really needed, and in fact can actually lead to what's called a broadcast storm. But we won't get into too much about that. But basically, if you have too many things being too noisy on your network, you will actually see network degradation as the switches and routers are busy trying to handle the broadcast traffic and can't necessarily let the legitimate traffic go through.
Moving on to the actual local network itself, I'm sitting here and I have a bunch of machines and I've connected them all to a switch. The switch is an upgrade from a hub because it is only sending the traffic from the intended transmitting device to the intended receiving device, as opposed to just spamming it to all of the devices and whoever needs to hear it hears it. And that's good because it limits the amount of, as you said, chattiness on the network, which is helpful. But there is some additional technology that's required on the switch to keep track of all of those individual endpoints. So, Steve, what is ARP and how is it used to keep track of those devices?
So an ARP table is, you can think of it just like a spreadsheet. It's a giant table that associates, in the case of a switch, it associates a port with a specific type of MAC address based on when it hears an end device. Computers themselves can actually have ARP tables as well. So if you're on Linux and you type ARP-A, you'll actually see a list of a computer if it can identify the host name, the IP if it's known, and a MAC address. And this is gleaned from any communication that your computer may have seen across the network. So if you do a ping, for example, and you do a ping scan across your entire network, it is likely that your ARP table will start populating. If, for example, you have a web server on a different host somewhere and you don't access it from your computer, that will not necessarily end up in your ARP table because your computer has no direct access or knowledge of that device.
In what circumstances can an ARP table be useful for troubleshooting? When might you come across a problem that you say, hey, that's something that I'd have to look at the ARP table, or I'd have to do something with the ARP table to resolve?
So I actually use my ARP table in a little bit of a different way for determining the MAC address for Wake on LAN. So one of the things that I have done in the past is I don't have a big list of all the MAC addresses of the things on my network. So there's a special packet called a Wake on LAN packet that if your network device is configured to, when it receives that packet, it will turn on that device. And so, for example, if I'm away and I don't have a good way to power on a device, I'll log into my desktop, which I make sure that my ARP table is up to date, and I will extract the MAC address for that. So there's all kinds of ways. What would you use your ARP table for?
I have run into a situation a couple of different times where the ISP will have an ARP table on their end of either a cable modem or I guess it all depends on the kind of interconnect that's being used, but their equipment interfacing to our equipment, and they have learned the MAC address of that piece of equipment and they cached it in an ARP table. And what I've come across a couple of times actually is you'll run into, hey, this isn't working. We've assigned the static IP address to the router, but for whatever reason, it's not able to talk on the network. It doesn't work. Call the ISP. What's going on? Oh, we had to flush the ARP cache, and once we've done that, now it learns the new MAC address of the equipment on the other side, and Bob's your uncle. Everything's back up and running. I guess, to be honest with you, I haven't seen that on a local network per se that I can think of anyway. Although a lot of that would get obfuscated, right? Because many switches, when you reboot them, they're going to build their ARP table back up. And so restarting the thing is like step one before we've ever even actually looked to see what the problem is. We probably restarted it to see. And so a lot of that stuff just, you're fixing it without knowing you're fixing it. Or I find a lot of people are fixing it without knowing they're fixing it. But it's interesting to know what's happening underneath the hood and the kind of problems that can solve. And so if you're having an issue with one device talking to the other and you believe you have all the IP addresses right and all of those things, you might want to check to see if you want to flush your ARP cache or restart that device to kind of start over and see if that resolves the issue. Another thing that I see people running into issues with sometimes is they'll assign an IP address to their computer. And so they'll assign 192.168.0.55. And then they go over to grandma's house and they sit down and they go, oh, grandma, let me show you this thing, 192.168.0.50. Well, it doesn't pull up. Well, why is that? And then they find that there's a different IP address that they have to use, and that IP address is a little different because it also requires some firewall rules to get to the inside of the network. Very confusing. What is the difference between public and private IP addresses, and why is that important for us to understand?
Yeah, so that takes us a little bit back into history. When they first developed IPv4, they thought that the 4.3 billion with a B addresses would be sufficient for any kind of networking. And what we soon found out was the adoption of networking, and specifically IP networking, meant that we were using those IPs faster than we anticipated. So what they decided to do was reserve a certain section of the IP address space for what we call private addresses. The private addresses are mostly going to be in the 192 range or the 172 range. There's also a 10.x range, but that is not likely to be found in the average consumer's house. This range is specifically known to routers to say, if I see this IP address, don't put it on the internet. It is not public facing. So when you've tried to call up in your web browser that 192.168.0.54 that you gave in your example from a different house, what's happening is the router that's connected to the internet sees that traffic and thinks, oh, it's not out on the internet, and then it searches its local network for that device. And if it doesn't find it, that traffic goes nowhere. So what happens is when you get an IP on the internet, you pull from this idea of a public IP address. This is an IP address that is assigned usually to your router. In some rare cases, you can actually connect directly to a modem, like a cable modem, and pull an IP on your laptop. But the idea is your ISP assigns you a single IPv4 address that can access the internet. Now you were saying, oh, well, how do I get traffic in? We're talking about port forwarding and things like that. What happens is there's this idea of NAT, Network Address Translation. So you've got an IPv4 address that is public. You call up that in your browser. That will then connect to your router, and your router says, well, I need to know what to do with this. If I see something coming in on port 80, I should send it to whatever host has the web IP inside. So you forward port 80 from, let's just make up a number. Let's say you are 1.1.1.1 on the public internet. So you type in 1.1.1.1:80 in your web browser saying, I want a regular HTTP page. That hits your ISP router modem that you have from rental. And it's, okay, which computer inside of my network should I send this traffic to? And so there's a rule that you can set up that says, if you see something on port 80, send it to 192.168.0.54. And that's what network address translation does for you.
So one of my favorite sites to use for determining what a public IP address is on a machine, you sit down, you're like, what is the public IP address of this site? Is IP Chicken. And the reason that I like IP Chicken is because it gives you the remote port. And so like what Steve was saying, when you have multiple machines that are connecting to the internet, they're sharing that public IP address. So that creates a problem on the inside of the network, because the router has to know, how does the router distinguish between Betty, who is browsing Gmail, from Joe, who also has Gmail open in a separate browser on a separate computer? Or maybe Betty has maybe Betty has Gmail open in one tab and Yahoo open in another tab. Both of them are using the same public IP address. So how can the router make that decision? And of course, it does that by dynamically allocating a port. And so you can actually see this in real time. You can go to ipchicken.com and you'll see up at the top, it'll say your current IP address is blah. If you look down under advanced, not only will you see the public IP address, but you'll see a little a field called remote port. And so just as an example, I've just done this on the computer in front of me, and I've been assigned port 33520, and that's specific to that instance, my computers, that web browser, that Windows connection to IP Chicken. If I open up an additional window and I go to IP Chicken again, now I've got two windows side by side. I get the same public IP address, but this time my remote port is 58430. And so when the router sees information coming in on 58430, it knows to send it to Noah's second window. And when it sees information coming on port 33520, it sends it to Noah's first window. And it's using NAT to allow me to have two simultaneous connections on my machine out to the world, as it would if you had multiple people being able to share that simultaneous connection. So NAT is a critical function of IPv4. We wouldn't be able to have a functional IPv4 connection with multiple machines on the inside without NAT. And that's going to change a little bit as we get into IPv6. We'll talk about that as we go on. Before we do, though, Steve, a lot of users right now are at this standoff point. We kind of touched on this in the last episode, where a lot of organizations are saying, we're not ready to jump into IPv6, you go first. And then the ISPs and the other companies are standing on that side going, yeah, you go first. And nobody really wants to make that plunge. And so slowly over time, ISPs have been rolling out IPv6 and companies have been rolling out IPv6. I believe the math is something like 25,000 addresses for every man, woman, and child on Earth. I mean, it's some insanely large number. But there is a problem, because until everybody goes to IPv6, we have to be able to be backwards compatible with IPv4. Talk to me a little bit about what that looks like if you have an IPv6 or an IPv4 and you want to be able to talk on the opposite, on IPv6 or IPv4, whatever the opposite is of what you're using.
Sure. So you were talking about the number of IPs per person.
Mm-hmm.
The total number of IPs that are available under IPv6 is 340 undecillion, which is 340 trillion IP addresses, which is,
wow.
If you're interested in a breakdown, some math wizard figured out that that's 567 sextillion IP addresses per square meter on the Earth.
Now, do you think that this is an honest question? Do you think it's enough? Consider when I say that, consider that every light bulb, every light switch, every one of these things in the future is likely to have an IP address. Do we think that's enough?
Well, I think that there's room to have additional, let's say RFCs. So there's additional room for, just like we brought in NAT for IPv4 to help us deal with some of these things. Mm-hmm. The way that the IPv6 address spacing works is that the first hex set, and we'll get into this in a little bit, but the first determines whether it's a public facing or a local link or what type of address it is. Okay. And right now we're only using if it starts with a 2 or a 3. And so, as you know, in hexadecimal, it can be up to 16 digits that first character can be. Okay. So if we're only using either a 2 or a 3 as public internet-facing things, that says to me, if we absolutely needed to, it seems to me that we have a bunch of other numbers that we could, in theory, tap into.
Okay.
Right. So I think there's room for growth. I think that there are people out there saying, like, this is galactic scale IP addressing, and maybe it is, maybe it's not. I don't really know. We used to think 4.3 billion addresses was enough.
Yeah, well said. So before we dive fully into IPv6, one last question for you: how is, in the traditional IPv4 model, we talked about what DNS is and the ability to look up IP addresses almost like a phone book. We've talked about what DHCP is, the server that hands out IP addresses. How are those things handled in the IPv4 world?
In IPv4, what happens is your computer boots up and it sends out a request for an IP. And normally what happens is your router responds with, I'm the router. Either it itself is the DHCP server or it knows where the DHCP server is. So the router responds with, here's your default gateway, here's what your IP is, here's sometimes even what your host name is, here's where you get your DNS server. And so that's how it works in IPv4. The system boots up, and when there's a network connection, there's a call out just basically a broadcast saying, hey, I'm alive on the network, somebody send me information. And the router usually responds with all of that information.
Moving into IPv6. Now, I'll be honest with you, this is not something that I have a tremendous amount of experience with, partly because, again, there aren't a lot of organizations that are hot to trot to do this. And so I've played with it. I've played with it at the ISP level a little bit, and then we've certainly used it in our data center. But it's not something I have a ton of hands-on experience. So this is going to be a learning experience for me as well, Steve. IPv6 Anycast. What is it? How does it work?
So first of all, we should say there are three types of connections or protocols that are being used inside of IPv6 as a general rule. And each of them have like sub-classifications, but we're not going to touch on that. So there's Anycast, and there's multicast, and then there's what we're going to call local, and that splits down into link local and unique local and a bunch of stuff like that. But to answer your question, what happens with Anycast? This is a unique idea, and it seems really foreign. So it took me a while to wrap my brain around it. What happens with Anycast is you can have multiple devices that have the exact same IP. And usually these devices are going to be a switch or perhaps a layer 3 switch or a router. And the idea here is when something goes out with the Anycast protocol, it broadcasts to that specific IP, knowing that there should be multiple endpoints that have the same IP. The purpose of this is to discover who is closest, because through some mathematics, what happens is when the Anycast is received by the receiving device, only the closest device will respond. And this is a way to help speed up the propagation of routes and things like that when you're talking about very large networks.
How about multicast and link local? How do those differ from Anycast, and what are the difference between those three? Where are the appropriate use cases for each one of those?
So multicast is more or less a substitution for broadcast, where a broadcast will actually just spam the entire network. Multicast actually has multiple endpoints, but it's not the entire network. So it functions in a similar way where it's attempting to determine which of its neighbors should receive the address. So in traditional thinking, a compute node, such as a computer or a phone or something like that, should be the intended recipient of a multicast, as opposed to a printer is probably not going to handle a multicast. And so multicast tries to only hit the endpoints that should actually receive it. So it's a kind of a combination of a broadcast and a targeted, one-to-one communication. So you were sorry.
Go ahead.
You were asking about the local link as well. So the local link address is something that for Linux users is probably going to be a little bit foreign, because in the Windows world there is this. I used to call it a garbage IP address. When you plugged in a Windows computer and you got a 169 network, that meant that it wasn't able to get an IP address from the DHCP server or wherever you're supposed to get your IP address from. This is actually called the link local network. And inside of IPv6, this is actually really important because every device must have a local link network. Every one of them will have this address. So when a network communication is happening between the router and an end device, this happens on the local link network. It cannot traverse subnets. It can't go across VLANs. It's literally just meant for local, like right around you. But every device must have one. So that's what the local link is. If you're trying to wrap your brain around how you might make a private range, similar to what the 192.168 range is for in the IPv4, that's where the unique link or the unique local link comes in. So this is as close as IPv6 is going to get to having that idea of, it's private and shouldn't go out onto the internet. So in IPv6, you're going to have it at least 2 IPs. You're always going to have a local link, and then you're going to have either or both. You can have 3, but you're either going to have the unique local for the LAN connection, or you're going to have the global, which is the one that allows you to get out directly on the internet. So you could have 2, 3, 4, 5, a whole bunch, all on the same interface. Unlike IPv4, where that can sometimes confuse things, IPv6 is specifically meant to handle that.
What, if any, are the privacy implications of doing it this way, Steve?
So there's a lot of implications here, both privacy and security. So by default, the IPv6 is going to give you a global address so that you can get on the internet. But not only that, your device will actually auto-configure itself for this. So whereas IPv4 required something to give you information, like hand you out an IP, for example, IPv6, as soon as the OS has been fully initialized, what it does is it actually auto-configures its own IP address based on some math that it does on your MAC address. So what this means is the host part of the networking. So let me back up just a little bit. Mm-hmm. Generally speaking, there is host bits, and then there's network bits. And this is how you determine how big that your yard is. So remember, we were talking about, or I should say our room. When we were talking about having a room full of people and not being able to hear outside of the room unless we had something to facilitate that, the host bits are the number that tells you how many people can be in that room before you need some sort of communication. Okay, so now with that understood, the host bits in IPv6 are based on your MAC address. What this means is, so what this means is there's a fingerprint that happens. Because every device has a unique MAC address, it means that the host bit that auto gets configured will be unique to your device, which means that it's really easy for them to know that, Steve's Nexus 5 is always Steve's Nexus 5, because it's always going to get itself the same IP based on the MAC address.
So in the IPv4 world, what we have lived with for a long time is that MAC addresses never transition a layer 3 device. So to break that down into plain English, your MAC address never leaves your router. It can go around your local network, but it will never jump from one network to another. It's not needed because without a routing table in place, there would be no way for the router to make a decision on to know which switch port that device is on and how to send traffic there anyway. And so that's all handled at the switch level. This changes that dramatically. And what's terrifying to me is that your computer is uniquely identifiable now, and that is available on the internet. Steve, do you know off the top of your head how spoofing comes into play? In the traditional world, if I spoof my MAC address, in fact, there are features in some operating systems that say every time I connect, Tails, for example, does this, every time I connect to a Wi-Fi network, it just generates a new MAC address and just makes it up. And so there's less of a privacy implication because I'm not using my real MAC hardware address. Would that be the same in IPv6, or is it doing something funky talking directly to the hardware?
So I don't really know too much about how it talks directly to the hardware, but I do know that if you are technically inclined enough, you can actually, let's say, alter the formula that auto configuration does. But that's going to be out of the reach of most people. Okay. Right? Just like MAC spoofing is kind of out of the reach of most people. There is a way to go in, especially under Linux, there is a way to go in and actually adjust the formula that produces the host bits of your IP address.
And a quick little plug for our favorite operating system on the planet here. If you click into Network Manager and click on your wireless network, one of the fields in there is cloned MAC address, and you can just set the MAC address. Where that can be useful for a troubleshooting standpoint is there are times I'll go to a hotel, and I will want to connect a device that doesn't have a web browser built in, and it's a device for either streaming media or it's one of my broadcast devices. And obviously when there's a captive portal being the website that you have to go to and accept the terms and conditions before it will let your device get onto the internet. The way that the access control for a lot of those captive portals is handled is through a MAC address. So laptop comes online, it accepts the terms and conditions, then that MAC address is whitelisted to be able to get onto the internet. And so when that computer with that MAC address sends packets to the router forwards them onto the internet. If it hasn't been whitelisted, if they've not accepted the terms and conditions, then it just doesn't let those packets ever leave the router and the user isn't on the internet and just gets redirected back to that captive portal page requiring them to accept the terms and conditions. So that presents a problem for people like me because I have devices that are they require access to the internet, but I have no way of accepting terms of conditions on those devices and thus getting that device's MAC address added to the whitelist. But because I'm a Linux user and because I'm a little technically savvy, right, I'll open Network Manager, I'll clone the MAC address of the device that I want to be authenticated onto the network with my laptop, open Firefox, accept the terms and conditions, then I disconnect from that network, reconnect the device that I want to have connected, and because that MAC address has now been whitelisted, the device has access to the internet. Then I reset the MAC address on my laptop back to whatever it was, and now that device is online, and Bob's your uncle. I've solved the problem. And so the ability to spoof MAC address, while it does require a little bit of know-how, is actually quite trivial once you look into it. And so it'll be interesting to see how that plays out in the IPv6 world. Now, something that gives me a certain level of intrepidation is the addressing in IPv6. For years, I have been able to walk into sites and just bang out IP addresses on the numpad with my fingers, and I can pull up printers and servers and all sorts of things because they're easy enough to remember. There's a couple of octets. There's only 255 possibilities in each octet, so I can remember most IP addresses. And we follow kind of a standard, and so that makes it even easier. IPv6 definitely follows a standard, but it's significantly more complicated. Steve, to the best of your ability, can you explain how the address is broken down and what hex texts are?
Sure. So we have octets in 192 is one of the octets. A hextet is similar to that, except it has 4 alphanumeric characters. So it can go so it goes from 0 to 9, and then it goes A to F. So that is the range of each one of those individual digits. The way the addressing works in IPv6 is that each hex has its own identifier, like a reason that when you look at it, you'll know what this means. So, for example, the very first hextet is the IANA assignment prefix, and we don't really need to know what that is. But more interestingly, when you go into the second and third hextets, this becomes a lot more specific. So the second hextet actually tells your geographical region, whether you're in North America, Africa, and so on. Then it goes down further. The third hextet will actually identify your ISP. And then the fourth hextet will identify the network that you reside on that ISP. So it gives a very precise idea of where you are in the world.
And so from a privacy standpoint, again, this is kind of terrifying because just your IP address is available to any other device that you're interacting with. And now, just based off of that IP address, there was a time where you can put an IPv4 address into a search, and it'll guess on where it is based on a number of factors, but it's not a for sure thing. This definitively, it's encoded into the address itself, and so anybody else that's interacting with you can tell with a reasonable certainty at least which ISP you're on and which region of the world you're in. Do I understand that correctly, Steve?
Yep, that's correct. And they, like I said, if they can figure it out, they even know which area of the ISP's network that you're living on.
That's scary. I'm not sure what to think of that yet. So I guess the jury will have to hold out on that until this gets a little more widely adopted and see if there are some ways that we can address some of those privacy and security concerns. So give me an example, Steve, of what an IPv6 address looks like and some of the shorthands that we can use to shorten them down. Because obviously, if we include all of the bits in it, obviously it gets to be a little bit unmanageable. It gets to be very long. Are there any shortcuts we can use to kind of shave it down?
Yeah, so we talked about the number of the hextets and how they relate to the IPv6 schema, right? So there's 1, 2, 3, 4, 5, 6, 7 hextets in the IPv6 realm. And so as you can imagine, that's a lot to remember. Like Noah was saying, it's really kind of difficult to remember all of that. There are a couple of things that can help you cheat. So you can, for example, if it has a leading 0, so if that hextet starts with a 0, you can just simply omit that because the 0 is implied, which means that if you have an address that has, for example, 0098, you can just put in 98 because the zeros are implied. If you have an entire hextet that is full of zeros, you can actually just simply put 0. If you have 2 hextets or more side by side that are all zeros, and this does happen, all you do is replace all of those zeros with 2 colons. So if you've got 000 colon 000, you just simply remove all of the colons and just leave all of the zeros and just leave 2 colons in the place. And that provides you this ability to compress down, provided that you have a lot of zeros in your address.
I think we briefly touched on this, but I want to circle back to it in regards to simplifying IPv6 addresses. What is the IPv6 equivalent of the 127.0.0.1, and how might we use eliminating those preceding zeros to make that shorter?
Yeah, so for people that don't know, the 127.0.0.1 address is your loopback address of the network. This is used to help you troubleshoot so that you can do activities on the network card without actually having an IP that other people can reach. So what Noah was asking is, what is the equivalent of this in IPv6? And the equivalent of this is actually all zeros except for the very last digit being 1. And you can prefix this by just : 1.
And so that makes it real simple to do network troubleshooting. And it's not. I would go as far as to say that it even extends a little bit beyond troubleshooting. I know that I've seen a number of different services that when they're installed by default, they use the 127.0.0.1 loopback IP address so that they don't have to be aware of whatever network implications exist in any specific site. They'll just know that because it's only talking to itself, and it enables you to ship a product that by default will work on any network, but you have the opportunity then to break that off and say, well, we'll separate the server and the client later on down the road and give the server an IP address and the client an IP address. But that allows you to combine them all into one and ship it. And so a great example of that is the Rivendell audio software that we use here at the station. And that's how it talks entirely over the network, but it uses the loopback IP address with the assumption that all of the components are running on a single computer. And that means that you don't have to have any network knowledge to get it up and running right off out of the gate. So, Steve, talk a little bit about, in an IPv6 world, what does it look like when a machine comes online? What is the process for a machine getting and speaking on the network?
Yeah, so this is kind of really fascinating. I think that they are really working towards a lot of automation here. So when a computer first boots up and the OS initializes, remember we talked about how it configures its own IP address from its MAC address. What then happens is it sends what's called a router solicitation. And so it basically sends a packet out over the local link and says, hey, where's my router? And the router then responds with its own local link network address as the default gateway. Unlike in the IPv4 world, though, The router doesn't give you anything more than that. So if you have DNS services, for example, on your network, you don't get that for free from the router. You actually have to configure that. You can set up what's called the DHCP v6, and the router can then help to accommodate the communication to an external DHCP server, which could have that address for you, like where the DNS information is, but that doesn't come for free. And so that part of it is really interesting. Once that connection with the network has been established, the next thing the computer does is actually sends out a neighbor solicitation, which is kind of like an ARP address. And what it's doing is trying to figure out who's around me, and do the people around me actually share my IP address? Did I accidentally configure myself too close to somebody on the network and we have a conflicting IP address, which statistically is so low that it's unlikely to ever happen, but they built in that kind of safeguard.
Steve, I want to talk a little bit about the security implications. Obviously, there are some privacy implications here, and I think as time goes on, those things will be addressed. And if not, I assume that those things will be worked around in the form of things like VPNs. And so, yeah, they'll know that the geographical location and the ISP and all those things are privateinternetaccess.com, and then they don't have lungs for anything else. And so the idea would be that we're safe, or at least that's what they would tell us. But from a security standpoint, there are other things going on. When IPv6 came out, one of the big things that people in the industry were excited for is the fact that IPv6 is designed to be connected directly to the internet. And that solves a lot of problems that manufacturers have been facing for years, because if you shipped a light bulb that you wanted connected to the internet through some cloud service, unless you had the user had the ability to configure firewall rules, or you were running a server that created a proxy connection so that you could access that machine from inside of a secure network and tunnel its way back out, it was very difficult for you to get that device to function in a wide variety of network environments. And IPv6 solves that to a degree because it is designed to be always connected, always online. Steve, what are some of the security implications of that, though? And how exactly does that work?
Yeah, so remember how we talked about how NAT isn't really a thing in IPv6? NAT has been a big blessing for people's security in general. So NAT itself is just kind of an obfuscation, but because it requires a firewall in order to help route traffic around, it has meant that most people have been secured by default. You know, you can go buy a Nighthawk router off of Best Buy or whatever, stick it in, and be reasonably sure that there's at least some level of firewall happening, that all of your devices are not directly connected to the internet. This doesn't exist in IPv6, or at least not to this point. What happens is, because devices are meant to always be connected, there is no port forwarding, which means that there's no requirement for a firewall. And so a lot of the privacy advocates, even as late as last year, have been talking about how the rollout from Spectrum and other ISPs putting these devices in people's home is almost negligent, because they're not providing any kind of firewall. They're just putting in an IPv6 modem router and walking away saying it's good and people can get on the internet and everybody's happy. But those internet connected devices are basically out there for everybody to see. All that's happening is traffic's being routed, but they're not being blocked. There's no firewall, and there isn't anything similar to what we call ACLs, or access control lists. And so what this means is, while corporations are employing things like Sophos and other types of firewalls to get around this, and they have the network infrastructure to pick up the slack from some of the shortfall, the average consumer isn't going to have or know that they need to have these sorts of protections in mind, which leaves a lot of vulnerabilities out there. And the only thing that's really, I'd say, protecting is too loose of a word, but you know, the only saving grace they have is that IPv6 is such a small target right now, and not very many people really know how to deal with it. And so that's the only thing that's really protecting these people right now.
How about firewalls, Steve? When it comes into firewalls and firewall security, right now that's almost kind of a default with IPv4 because, and some of this is confusion in the technology. It's not really the firewall, it's really more of NAT, but oftentimes the firewall and NAT are kind of rolled into one because if we're going to pass traffic from the outside to the inside, we may as well create some rules to do that. Is that possible in IPv6? And if it is possible, is it turned on by default or is it something that you have to add on your own?
To my knowledge, the devices are not shipping with the firewall. So the privacy and security advocates that I kind of follow online are saying, go get a firewall and stick it behind the router. Or if you can, just get the IPv6 modem from your company and stick your own like pfSense or, even if you want something like the Nighthawks, or because they're not the cheapest device out there, they actually have the ability to do either IPv4 or IPv6, and they do have a firewall built in. So there is some possibility of that, but like I said, to my knowledge, the last I checked, most of the consumer grade stuff that's coming from the ISP doesn't have a firewall.
Steve Ovens, thank you so much for taking the time to come on and discuss this. I think networking part 2 is another success. I know I've learned a lot about IPv6 being here. We'll have to dig in and do more. Again, if you have questions, if you have thoughts, if you say to yourself, this stuff is so interesting to me, but I need to know X, or I want to know more about Y, we invite you to send in feedback. Send it in to live@asknoahshow.com. Steve goes through the emails, he reads all of those, and then we formulate those into different categories and organize them so that we can take different topics and say this will apply to a wide range of people. So you guys have spoken up and said, hey, we're interested about networking, and that's how these segments come about. So please continue to do that. Continue to send in feedback. And Steve, you always have an open invitation on this program. Thanks so much for joining us again. Another round of networking. We'll get you back on the program soon.